Yeah, I guess it's a good time to start. Hi everyone, welcome to Theory Lunch. We have Professor Nihar Shah to talk about two F words in peer review. Yeah, go ahead.
Thanks, Praneeth. And hey, everyone. I'm excited to be talking today in the Theory Lunch. In our group, we are looking at various problems in peer review and related applications. And there are nice theoretical problems that of algorithm design. We also do experiments and are having a lot of real world impact as well. So today I'm going to talk about two specific problems that we worked on. So peer review, many of you would be familiar with the peer review of papers in various conferences or journals, but peer review is also used beyond that. For example, billions of dollars worth of grants are awarded annually based on peer review. It's used for promotions and employee evaluation in various organizations. And any challenges in peer review hence can significantly hamper scientific progress. It's well known that academia has a Matthew effect of rich getting richer. And so problems in peer review can in fact are known to affect careers of researchers. And a really important point is that challenges in peer review also harm the public perception of science. So many of you might know of that famous paper which incorrectly claimed a causal link between vaccinations and autism that got accepted, and that started a huge anti-vaccination movements and so on. So hence our goal is to address challenges in peer review. And today I'm going to talk about two challenges, which are these two F words, fraud and feedback. So throughout this talk, please feel free to interrupt with any questions. You can feel free to either just unmute yourself and shout out the question, or use the Zoom raise hand feature, or type it on chat. I have another machine where I'm monitoring chat as well. But please ask questions. All right, so let's start with this issue of fraud. And this is joint work with Steven Jackman, Hanrui Zhang, Ryan Liu, Fei Fang, and Vince Conager. So what kind of fraud are we talking about? Well, so recently there have been discoveries of the following kind of fraud. Here, there's a reviewer who says, hey, who tells an author? The author is this reviewer's friend. So the reviewer tells the author that, hey, I'll try to get assigned your paper and I'll accept your paper. And in return, you can do me a favor, maybe in this conference, maybe elsewhere, and so on. Okay. So these kinds of collusions have been discovered in various places. For example, one of the first places where this was discovered was in computer architecture conferences. And in fact, this had extremely unfortunate and sad consequences. But there they found that a group of reviewers and authors, they tried to get assigned each other's papers and then accept each other's papers. And this discussion here concludes by saying that our peer review process is not set up to combat such collusion. And subsequently, such collusions have also been uncovered in other conferences and in grant reviews as well. So now our goal is to address this problem, or at least mitigate it. And towards this, one key point to note is that one main aspect of this collusion is that the colluding reviewer tries to get assigned the target paper. So now,
could I ask a quick question?
Yes, go ahead.
I mean, this is maybe a tangent, but was there a consequence for these authors and these PC members? Like, what was the consequence?
That's a great question. So in this particular investigation, there was one person who was banned from submitting to ACM venues for 15 years. Although that ban came after humongous protests and so on. Initially, there was almost nothing. But that was just for one person. And this person's name has been revealed. For others, I think there is some penalty, but their names are not out in the open. So they might still be continuing to do this, in grant reviews and elsewhere.
Yeah, I also want to mention actually, so I'm chairing a conference, and I'm aware that ACM is actually, they are pretty concerned about this, and like for this conference that I'm chairing, ACM CCS, like the SIGSAC made some new policies regarding like the integrity for the review process.
Great, yeah, that sounds great. Thank you, Elaine, and thanks for the question, Danny. Yeah, please, everyone, please feel free to interrupt and ask more questions. All right. So let's see how this reviewer assignment happens in a lot of our conferences. So a lot of our conferences have grown large enough that we need some automated systems to do this assignment. These automated systems typically operate in two stages. The first stage involves computing what are called similarities. So for every paper reviewer pair, let's say paper P and reviewer R, you compute what's called a similarity score, which we denote as SPR. So this is a number in 0 to 1, and a higher similarity score means that we envisage a better quality review by this reviewer R for this paper P. Now, there are various ways in which this similarity score is computed. For example, you use natural language processing techniques to match the text of the submitted papers with the reviewer's past papers. Sometimes some conferences ask reviewers and authors to choose subject areas, and you match based on that. Or some conferences have reviewer bids, and we'll come to that in a couple of slides from now. So based on one or more of these techniques, you compute these similarity scores. And you set the similarity score to say -infinity if you know there's a conflict between this reviewer and one or more authors of the paper. For example, if the reviewer is the author of this paper or is a colleague or collaborator of this author, then you set this as -infinity, and so that this paper is not assigned to this reviewer. Now, using these similarities, then we go to the second stage, where they're used to actually assign the reviewers to papers. Now, how's this assignment done? So here's the way in which it's done by far most commonly. So you do the assignment by solving this optimization problem. So in this optimization problem, the assignment itself is this optimization variable. And the objective is the sum over all papers and reviewers, the similarity SPR, and the indicator that paper P is assigned to reviewer R. In other words, this objective is choosing the assignment which maximizes the sum of the similarities of the assigned paper reviewer pairs. And the constraints are just load constraints. That is, every paper should get at least 3 reviewers, and no reviewer should get more than 5 papers. Right? And this is easy to solve using standard methods. And this is what's used very commonly. Right? Questions? All right. So now with this context, let's look at some possible defenses against collusions that have been explored. So one obvious defense is conflicts of interest. That is, figure out who the collaborators or colleagues are for any author, and don't assign papers to those collaborators or colleagues. This is routinely done in our conferences. But a key challenge here is that the colluders may not be known collaborators or colleagues. For example, in this computer architecture investigation, they found that the colluders, in fact, went to great lengths to escape these conflict of interest detectors. So they say that there was a chat group of a few dozen authors who worked on common topics, but they were careful enough to ensure that they never co-author papers with each other so that they don't end up in each other's conflicts lists. Moreover, they went to the extent that even if they collaborated, one of them gave up the authorship of the paper so that they don't appear in each other's conflicts of interest lists. So yeah, these are challenges with this defense. A second defense which people have tried out is the following. So this defense assumes that the quid pro quo happens in the same venue. That is, for example, if people A and B are colluding, then A helps B and B also helps A in the same conference. That's what this assumes. And then there are papers which look at modifying the assignment procedure so that there are no cycles, or at least small cycles in the assignment. Okay, so if I review your paper, you will not be asked to review my paper. However, an obvious challenge is that this quid pro quo might happen elsewhere. Right? A might help B in conference 1, and B helps A in maybe a grant proposal review. And so this won't really work. So the third defense looks at what are called bids. So let's come to that. So after the conference submission deadline, all of the reviewers are asked to log into the conference management system. The reviewers will be shown a list of all the submitted papers, and each reviewer can indicate for each paper whether they are willing to review, indifferent to it, or unwilling to review. And this information is used to compute the similarities SPR, which are used in the assignment. Okay. And some of our experiments, as well as some other experiments by Wu et al., have found that by strategically bidding, a reviewer can significantly increase the chances of getting assigned a target paper. So given that, there's this work by Wu et al., which tries to mitigate this issue. And their approach at a high level is to look at the bidding data. They'll also look at data from the natural language processing text similarities. And then they'll identify the bids which are outliers with respect to the other data. And then they'll remove those bids. At a high level, this is their idea. Questions?
So Nihar, how do they figure out, what's an outlier?
Yes, great question. So what they do is they build a machine learning model that can predict bids from other sources of data. And so then in the validation set, whatever you cannot predict well, they seem outliers and those are removed. Great, thank you. Other questions? All right, so what are the challenges here? Well, so there are other aspects of these automated systems that we have beyond bids. Like, for example, as we discussed, we have these subject area choices or reviewer profiles, which are used to do this text matching. All of these, they're known that these can be gamed. For example, there's this nice paper which talks about TPMS. TPMS is a very popular system used for text matching to compute similarities. And they say this can be gamed through rare keywords. Moreover, if you're interested in security, there is this very nice pair of papers, very interesting pair of papers, which discusses these what are PDF embedding attacks on the text matching system. So they show that these attacks can be successful in real world systems to get assigned target papers without any human ever knowing it. Okay. So overall, it's not just the bids. There are various other aspects in the assignments that could be gamed. And then finally, a hard challenge is that sometimes the colluding reviewers may already have expertise for that paper. And so they can be assigned even without manipulating the bids. And this was also found to happen in that computer architecture investigation. Right? Questions? So given all of this, our approach was different. So we were not looking to—
I didn't understand something about the PDF embedding in question. I don't understand the PDF embedding.
Right. So what they do is, so our papers are in Adobe PDF format, right? And in that, the Adobe PDF allows you to embed fonts. So the attacks, what they do is the following: they'll construct fonts such that to a human it looks like something, and to an automated parser it looks like something else. And so if I'm writing this paper to any human, it'll look like I'm talking about peer reviewer and fraud. Whereas if Danny, if I want my paper to get assigned to you, then I'll embed a font such that an automated parser reads the text which is commonly found in your papers, and so will match to you. So that's the basic idea behind these PDF embedding attacks.
And this is something that people are doing?
We don't have people are doing, hopefully not. These security researchers, they constructed, so these are security researchers who constructed these attacks, and they demonstrated on certain systems which are actually being used in practice that you can get assigned target papers.
Fair enough.
Okay, but the problem with that method is it's very easy when you find somebody doing it. It's almost a confession of cheating. But anyway, thank you.
Sure. Yeah. Thanks for the questions. Other questions? All right. So we thought of taking a different approach. So our thought process was, hey, there are so many ways that these systems could be gamed that, hey, let's adopt a mitigating strategy. So we just want to make sure that for every paper, there's a good chance that you'll have independent reviewers who are not colluding. And so at a high level, we want to impart diversity in the reviewer assignment via some sort of randomness or constraints. That's our high level approach. Now, towards this, we've written a paper and there are a bunch of results in it. I'm not going to go through all of them. I'm going to talk about this first result for two reasons. One, that it's simple enough that I can show some nice pictures for a proof and so on. So I enjoyed making the slides and hopefully you'll enjoy looking at them. And second, it's been impactful. So it's actually deployed in the real world and being used. So let me come to that. So recall we discussed that a key part of this collusion is that a reviewer tries to get assigned a target author's paper. And so how do we ensure that this doesn't happen? Well, a simple idea is, hey, let's just assign reviewers to papers uniformly at random. Right? That will clearly mitigate this issue because the chances of a colluding reviewer getting assigned a target paper is very small, irrespective of what the reviewer does. There's an obvious problem here that the assigned reviewers may not have expertise for that paper, and so you'll get probably junk reviews. So now, instead, what we can do is trade off between the randomness and the expertise. And this is what we do. So let me just formalize this. So the program chairs or the organizers of the conference can specify a matrix, which we call Q. So the rows of this matrix are papers, the columns are reviewers, and each entry is in 0 to 1. And given this matrix Q, what we want to ensure is that the probability with which any reviewer R is assigned to any paper P is at most QPR, the PRth entry of matrix Q. Okay, this is what we want. And in practice, the program chairs could just choose Q as a constant matrix. And so far, this is what people have done in practice. But if you have some other information or some other requirements, you need not choose Q as a constant matrix. you could incorporate that information within Q. Okay, so our goal is to choose a random assignment in practical time, which can scale up to tens of thousands of papers very quickly, so that these probability constraints are met. And then you want the best possible assignment and expectation. That's our goal. So towards this, how do we go about doing it? Well, first, we'll compute what we call a fractional assignment. That is, the optimization problem on the slide is the same as what we had earlier, except that the assignment is now replaced by this variable f, which can take real values. And the key difference is the last line, where instead of f being discrete valued 0, 1, it can be any value in 0 through q.
Nihar, I don't see your slide changing.
Oh,
yeah, I can see now.
Do you see the proposed randomized assignment slide?
Yeah, I see the slide now.
Okay, perfect. Thank you. And now you solve this and you get an f. And from this fractional assignment f, we'll then sample an assignment at random so that all the load constraints get satisfied. And f becomes the marginal for the probability of assignment. That is, the probability with which any reviewer R is assigned to any paper P is exactly FPR. Okay, so we want to do this sampling. And given this framework, now some guarantees follow quite easily. So this does meet the Q constraints. Right? FPR is at most QPR, and FPR is the probability that the reviewer R is assigned to paper P. Right? So now we have that the probability that the reviewer is assigned to the paper is at most QPR. The assignment in terms of the objective that we had is optimal in expectation, because F is just the marginal. So it's the expectation of the indicator. And this is the algorithm that we'll have is polytime, and in fact, it's practical time. So it's been used for many thousands of papers, and it's very fast.
Okay, but this is just a fractional algorithm, right?
No, the whole thing, the sampling as well. So the whole thing.
How did,
So
but you didn't talk about the sampling.
I will. Yes, done. Yes, I'm going to talk about it next. Yes, thank you. Yes. So the whole thing, like 1 and 2 together, this is practical time. It's very fast. Okay, great. So I'll talk about 1 and 2 both now. Thank you, Danny. So to go into details of 1 and 2, we'll do a simple example or a simplified example. So let's say that Q is a constant matrix. All the entries are a half. Let's say the number of papers equals the number of reviewers. And let's say each paper is reviewed by 1 reviewer, and each reviewer reviews 1 paper. So now this first step, I've just written it for that simplified condition. So you see that the load constraints are all 1. And if you see the last constraint, we have FPR less than equal to 0.5. This is because we had set Q as a constant matrix with values 0.5. So now you can see this is a nice linear program. You can solve it efficiently. And this first part is straightforward. And you have a nice property as well. So what's this nice property? I claim that there is an optimal solution which our optimization packages will find, where FPR is either 0 or a half for every PR. So let's prove this. So let's just do a change in variables. So let's say F tilde is twice of F. Yeah. So now in the program on the left, I'm going to do this change of variables and replace f by f tilde divided by 2. So can you see the change? Oops, yeah, okay, it came up. So now this updated or the change of variables, after the change of variables, the optimization problem satisfies totally unimodular matrix conditions. Right? So if you're not familiar with these TUM conditions, essentially they guarantee an optimal solution which is integer valued for such a linear program. So with these TUM conditions, we'll get a solution that is integer valued. So an optimal f tilde, which is integer valued. Now, since f tilde is between 0 and 1, the optimal f tilde will be either 0 or 1 for all PR. Okay. And since f tilde is twice of f,
Is total unimodularity the same as having a vertex solutions?
yes.
Okay.
Yes, it guarantees that the solution is at a vertex and our vertices are all integer valued.
Or maybe sort of technically so all the vertices are integers. Sorry, yeah, exactly. It's always the case that the extreme points of the LP are at vertices, right? I just wanted to.
Yeah. Yes. So here, yeah, thank you. So FPR hence is either 0 or a half. Okay, for all PR. Oops. Okay. So now we're going to use this nice little property in our second part. So now here, what we wanted to do was from our given F, we wanted to sample an assignment at random so that every paper has one reviewer, every reviewer has one paper, and FPR is exactly the marginal. That is the probability with which reviewer R is assigned to paper P. So how to do that? Well, so if you're familiar with the Birkhoff von Neumann decomposition, then this might seem very familiar. However, like what we want doesn't directly follow from Birkhoff von Neumann. Our work builds on and simplifies an algorithm by Budish et al. From 2009. So let me describe our algorithm in some pictures. So here we'll construct a bipartite graph where reviewers comprise one set of nodes and papers comprise one set of nodes. The edges will represent the support of F. So for any paper P and reviewer R, we put an edge between them if FPR is a half, and we don't put an edge if FPR was 0. And this is where we used our result, which we proved in the previous slide. So now, one can easily observe that this is a two regular graph. Why? Because FPR is either 0 or a half. And then we have a load constraints which say that at any node, the FPR should sum to 1. Right? So you'll have just two edges, exactly two edges of every node. And given this is a two regular graph, we can write down the edges as a union of disjoint cycles. So let's say we did that. We have this blue cycle, red cycle, and green cycle. And then we'll pick any cycle, let's say the blue cycle. We'll traverse that cycle, and then we'll denote alternating edges as dotted dash, dotted dashed. Then we'll toss a coin. With a probability half, we'll take the dashed edges and put that in the final assignment. Or otherwise, we'll take the dotted edges and put that in the final assignment. Now we'll walk the next cycle. Again, partition adjacent edges as dotted dash, dotted dashed. And then again, toss a coin. With probability half, we'll take the dashed edges. With probability half, we'll take the dotted edges, and so on. Okay, so this is the algorithm for this simplified setting. And now, just by this description, the guarantees immediately follow. So first, it does satisfy the marginal probabilities of a half for the support. Why is that? Because each edge was either dotted or dashed, and each edge hence had a 50% chance of being selected for the final assignment. Okay. And the second guarantee is that all degrees are 1 in the final assignment. And this is also because every node had 2 edges. One would be dotted, one would be dashed, and we'll pick exactly one of them. Okay. Questions?
Yeah, so in order to generalize this, is it just by like using this result that a regular bipartite graph can be decomposed into matchings?
Yeah, it gets a little more annoying than that. That's because we deal with arbitrary queues, and so we have to do a little more annoying work than that. So, like, the commonality still is that we walk around cycles, and then every cycle will toss a coin and select a subset of edges. However, now what might happen is that we can't just write it down as a disjoint union of cycles. Like, an edge can appear in part in one cycle, in part in another, and so on. So it gets a little more annoying. This Q as a half makes everything much nicer, that we can present it on the slides this way. Yeah, thank you for the question. Other questions?
So
all right.
What's the
Yeah,
typical
question.
value of Q that's chosen in the conferences that used this?
So, could you say that again?
What is the typical value of Q chosen in the conferences that use this system?
Yes, very good. So let me come to that next. Okay. So we discussed so far this part about randomness, right? The Q matrix specifies the amount of randomness that we want. And then our discussion was kind of how to choose this assignment at random and so on. So our initial goal was to trade off expertise and randomness, right? So now how does this trade-off work? And how do you choose this Q, and what are the Qs chosen in practice? So in practice, our algorithm's really fast. So what you can do is that the program chairs can beforehand decide on a set of possible values of Q. Let's say they can say Q as 0.1, 0.2, 0.3, 0.4 until 1. And then for every Q, we can plot the sum similarity value on the y-axis. So this is the plot from data from ICLEAR 2018 conference. The x-axis is the value of Q. Q is a constant matrix, and that's the value. The y-axis plots the objective value, the sum similarity, as a percentage of the deterministic one. And so the program chairs can see this trade-off and decide where they want to operate on this trade-off. So in practice, I know that people have used 0.5, 0.52, I think 0.7 or 0.75. So these are values that people have used in practice. Questions? So this this algorithm is really fast. So even for, say, something like 10,000 papers, the program chairs can run it, look at the assignment, see if they're happy with the expertise. If not, then they can choose a different value of Q, and so on. So it allows the program chairs to do this quickly. Questions? So this is deployed in the Open Review conference management system. We recently put this into the Microsoft CMT scripts as well. And this has been used at several venues. So what are some open problems? So there are also other kinds of dishonest behaviors that have been found in peer review, and algorithms to address this kind of dishonest behavior are also of interest. Specifically, even just detecting any such kind of fraud is also useful. And there are also various questions about policy, law, and ethics. And this also comes to some of the questions that were asked at the beginning of the talk. So, should algorithms be allowed to flag certain kinds of behavior, given the biases, etc., we know that machine learning has? And if so, should any human be able to see it? Or should the assignment algorithm just disable such assignments or bids, etc.? And if you discover some reviews are suspicious, then what should be done with them? If you discover clear-cut fraud, then what should be done there? Right? At least I think the answer to the last question is quite clear, that if there's clear-cut fraud, then there should be significant punishment. However, many conferences don't have those systems. So currently, if there's a very, very clear-cut issue of, let's say, plagiarism, the worst thing that will happen to the authors is that that particular paper will get rejected from that particular conference, period. No blacklists, nothing else. So these are all questions that I think we as a community should discuss. So this concludes the first part of my talk on fraud. I'm very happy to take any more questions. If not, then let me move on to the second part of my talk, which is on.
I have a question. Yes. Like, have you talked to Eddie? Like, it would be nice to have it in hardcrap as well.
Yeah, so I have emailed Eddie a couple of times, but I guess he's busy. But yeah, I'll be happy to facilitate it in hardcrap. Just getting hold of Eddie may not be so easy. Yeah, and Elaine, we can talk offline about it. If we can get that done, I'll be excited to join, to contribute to this effort. Thank you. Other questions? All right, so the second part is about feedback. And this is joint work with Jingyan Wang, Ivan Stelmach, and Yuting Wei. So in any real world system, a feedback is really crucial. Right? We do research and development, testing, deploy it, and then we get feedback from the real users. And then we use that to loop again. However, one might argue that this feedback loop in peer review is somewhat questionable. So how do we evaluate the peer review process? How do we evaluate specific reviewers? Right? There has been a lot of debate in various communities. Some people think that the program chairs should evaluate and so on. There is one argument made by many people which says that authors should be asked to evaluate the reviews. And the argument is that the authors know their papers best. And so you could ask them to rate the reviews. Right? A problem with this is that authors are highly biased by whether their own paper was accepted or rejected by this reviewer. And there are various studies on this, which show that the satisfaction of the author with the review had a very strong and positive association with a reviewer recommending acceptance. And they also find that the actual quality of the review had a very low association, or there was no association at all. And so our goal in this part is to debias author provided feedback. And actually, there's a similar problem in teaching evaluations. So many of us faculty, we teach courses, and many of you students are asked to rate the course or the instructor's teaching effectiveness. And even there, it has been found by many studies that the students' ratings of the faculty are highly biased by the grading leniency of that faculty. There are various studies which find that this association of grades on the student provided evaluations is substantial and statistically significant. And then there's also some literature which says that this introduces incentives for inflating grades. Right? Instructors now want a better course evaluation, so they'll inflate the grades. And so this problem is also similar to what we discussed on the previous slide. And so in our work, the general framework also looks to address this problem. So here's the problem formulation. So you have a set of items that are to be evaluated. Let's say these are reviews or courses or review process, etc. So you have a set of items. And each item I, we assume has some unknown true quality. Let's call it X star I. Now for every item, we have a set of evaluators. So this could be authors in the case of peer review or students in case of courses. And now if an evaluator, let's say evaluator J, rates an item I, we model the observed rating Yij as shown on the slide. So Yij is assumed to be X star I, the true quality, plus a bias term, okay, bias Ij, plus a noise term, noise Ij. And this bias term is what will capture the issue that I mentioned in the last two slides. So for the noise, we assume this is IID, zero mean Gaussian with an unknown variance. And a key part of the formulation is about modeling this bias. So let me go into that in more detail. So in peer review, let's say these are the set of authors, and you know the number of accepted and rejected papers for these authors. Okay. For example, the author on the leftmost part of your screen got 2 papers accepted and 0 rejected. On the top left, that author got 2 accepted, 1 rejected, and so on. So now let's focus on these 2 authors. And the leftmost person had 2 accept, 0 reject, whereas the top left had 2 accept and 1 reject. So one might think that the leftmost person is at least as well off as the top left person. And hence, we model the bias as the bias of the leftmost author is greater than equal to the bias of the top left author. Okay. And so on. Likewise, in a course, let's say these are the various students and these are their scores.
But the bias, wait a second. The bias is the function. Isn't the reviewer the one who's biased, not the author?
Yes, so this is the author. The author is evaluating the review. So Yij is the...
Oh, this is a, oh, I missed that. Something.
Great.
Yeah, you were, this is about reviewing, about evaluating the reviews. So you're,
Perfect.
okay, okay.
Perfect. So the set of items that are to be evaluated are reviewers or reviews or courses. And the evaluators are the authors or students. Great. Thank you for the clarification question. Other questions? All right. So in case of courses, so let's say these are students and these are their scores. And we assume that the bias is monotonic according to their score. Now, one important aspect to note is that the conference organizers or program chairs, they know the outcome of each author's paper. So they know who had how many papers accepted and rejected. Likewise, in courses, the university knows the outcomes of each student grade or score. And so what we assume is that the biases follow a known partial ordering. Okay, this is a question in chat. Students have only one eye, where authors have two. Good catch, Danny. They're going to graduate and get the second eye in the graduation ceremony. Good catch. I when making this slide, I don't think I had noticed that. I copy pasted some Indian pictures. Okay, so we assume that. Sorry, go ahead.
I like your answer.
Thank you. So we assume that biases follow a known partial ordering, right? Okay. So specifically, how do we? So here's the generative model for the biases. So you generate IID, zero mean, Gaussian, random variables for all BIJs. And these have variances which our estimator does not know. Okay, they're IID, but an unknown variance. And then you permute them to align with the known partial ordering. So this is the assumed generative model. So think of it as just IID, zero mean Gaussian with unknown variance, but they're ordered according to the known partial ordering. Oh, sorry. And now the goal is that we are given the YIJs and we want to estimate the X stars. And so that's the goal. All right, so let me describe our proposed estimator. And this estimator is this optimization problem on the slide. Here, you first have an argmin over X. So X is what we are trying to estimate. This is the true quality. And then we don't know BIJs. And what this is also doing is minimizing over BIJs, where these variables BIJs are restricted to obey the known partial ordering. Okay. Now, what is this objective here? So the first term of the objective captures the noise. So this is kind of like least squares. Recall that we had assumed Yij equals X plus B plus noise. Right? So this is just the noise term, Y minus X minus B. And this is just like standard least squares. And then the second term captures the bias. Okay, so it regularizes with the bias. And we have this hyperparameter lambda, which I'll talk about in the next couple of slides. Okay, but this is the estimator, minimize over X and B, where B obeys the known partial ordering. We have two terms capturing the noise and the bias. So what we show is that under some technical conditions, we show that when there is no noise, if you set the right value of lambda, that is lambda is 0, then the estimator is consistent. Okay, so it reduces to something nice because in this setting, the sample mean, which is a very common estimator, that is not consistent. On the other hand, when there's no bias, if you were to set the right value of lambda, let's say lambda is infinity, then this becomes equivalent to the sample mean. which is nice because we also know that when there's no bias, sample mean has some amazing properties, right? So if you were able to set the right value of lambda, then nice things will happen. However, we don't know how to choose lambda because we don't know the amount of bias, we don't know the amount of noise. So we have to choose lambda in a data dependent fashion, right? So now how do we choose a hyperparameter in a data dependent fashion? Well, a natural idea is cross validation, right? However, cross validation suffers from a key challenge in our setting. So let's say we try to use standard cross-validation techniques to choose lambda. So let's see what happens. So how would we do cross-validation? Well, we'll take all the YIJs, right, all the data we got, and partition it into a training set and a validation set. Now for each value of the hyperparameter lambda in some set, on the training set, we'll estimate X hat and B hat from the objective that we had. And after that, we'll go to the validation set, plug in this X hat and B hat, and measure the validation error. This is standard cross-validation. However, we can't really do, okay. And finally, we'll choose the lambda, which has the smallest validation error. So this is standard cross-validation. A big challenge was that we can't really do this in our setting. Why is that? We separated out the YIJs into a training and test set. And so from the training set, you would get B hat IJs on the training set. And this cross-validation technique will try to take that and plug into the validation set. But you can't do that because the B hat IJs for the validation set are different from that in the training set. So you can't just take it here and plug it there. And so a large part of our work was to address this challenge. So as some of you who've worked in cross-validation might know, like, proving things for cross-validation itself is hard. And then on top of it, we had to deal with this issue. So our idea was that we'll take the B hat IJs in the training set, and then we'll use the knowledge of partial ordering, because we know the partial ordering of the biases, to get the B hats in the validation set. So this is the idea. And based on that, we show that nice things happen. That is, the lambda chosen is actually a good value of lambda. So that's at a higher level. So I'm almost out of time. So essentially, yeah, we have some semi-synthetic experiments where things work well. I'll go quickly because we're out of time. Our estimator with cross-validation outperforms the mean and median, which are the only two other estimators we know. And so I'll move fast, and it chooses good values of lambda. Yeah. So overall, there are various open problems here. We don't have sample complexity guarantees, and it will be great to have them either for this estimator or design new estimators for which we can show such sample complexity guarantees. Our models are admittedly somewhat simplistic. This was the first crack at this problem. More nuances will be useful. And also there are questions about what incentive structure does this kind of a system lead to? And what are good, more generally, evaluation metrics, etc., for peer review algorithms and policies? So to conclude, we discussed two key challenges in peer review: fraud and feedback. There are many more open problems. There are very interesting and challenging theoretical problems that are directly useful in practice and can have major real world impact. So if you're interested, there is an overview that I've written here on the link on the screen. With that, I'm happy to answer any more questions. And I'm also excited about this topic. So and if anyone's interested, I'm very happy to chat offline as well. Thank you. If there are any questions, any more questions, I'm happy to answer them. Okay. If
So,
not,
Nihar,
then
are you
yeah.
also
Go ahead.
looking at questions of how, like, a group of people can kind of gang up on papers and
Yeah. So
kind of kill it that way?
Yeah, so that's a great point. Some people call it torpedo reviewing. That is, you try to review a paper just to reject it. Maybe because you don't like the author, or maybe because you don't like that particular line of research. The methods that I discussed in fraud also help for that. So again,
Sure.
because we have randomness, even if somebody tries really hard to get assigned the paper to torpedo review, there's a chance they won't get assigned.
Right. Cool. Yeah, I had some thoughts on possible, there are some ways in which you could randomize the matchings even more, because matchings tend to have these positive correlations kind of thing. Where so there is some work, you probably have seen it, but I'll point it out anyways. I'll send you a mail and then we can
That's awesome. Thank you
see
so
what
much.
Absolutely.
Thank you.
Okay.
Thank you. I look forward to it. Thank you so much.
Excellent. Thanks, Nihar. I'll see you.
Thank
Bye-bye.
you, Anupam. Any other questions? If not, then thank you for coming to the talk, and I'm always excited to chat about these problems. So if you're interested, feel free to shoot me an email.